So here we are. We need to have a discussion about how calculus can help us deal with corned beef hash. Believe it or not, this is an introduction to our applied optimization lesson, and it has a lot to do with the corned beef hash. So let's jump right into a corned beef hash problem. The Langer Food Company requires that its corned beef hash containers have a capacity of 54 cubic inches, have the shape of right circular cylinders, and be made of aluminum. To minimize production costs, the cranky boss asks you to determine the radius and height of the container that requires the least amount of metal. Since your job depends on it, you turn to calculus for help. What dimensions will you give the boss to save your job? So the idea here is that if we can minimize the amount of material that we use to make the containers, we will save money. And we can use calculus to help us with that. So we'll come back to the hash container problem in a second, but what I want to do first is talk to you about our strategy for solving problems like this. These are optimization problems. So in our case, we are trying to minimize the amount of metal that we need to build these cans. That's optimization. You could also be maximizing some quantity, and that would be optimization. These are going to feel similar to the related rates problems that we started recently, but they're different. There's some key differences that we have to pay attention to. But it starts out the same. We want to read the problem and understand it. This may require reading it more than once. As you're reading it, write down important information like what is given, what is the unknown quantity to be optimized. In other words, get organized. Once you've done that, you may need to draw a picture. If you draw a picture, you should label any part of that that may be important. Man, I stumbled through that sentence because my phone beeped while I was trying to spit it out. The idea is that you draw the picture and label anything that's important. We're also going to introduce variables to the situation. Often those can be placed on your picture. We're either going to introduce those as an equation or as an algebraic expression. Finally, in step 4, we're going to write an equation for the unknown quantity. In this situation, we're going to have two equations, most likely. We'll have an objective function. That's the thing we're trying to optimize. And we'll also have what we call a constraint, which relates the variables in our problem. Because when we get down to step 5, we're going to need a function in one variable. We can't have a bunch of extra variables in our problem, so we will use the constraint to eliminate some variables. That's a key difference from the related rates problems. We had equations in our related rates problems that had all kinds of variables, and we would take the derivative implicitly with respect to time. For these problems, we need a regular old function of x and y so that we can take a standard derivative. Once we take the derivative, we're going to find critical points and then also endpoints, and we will test those to determine the optimal values. It might be the minimum value, it might be the maximum value, and then finally, we want to make sure we're answering the question that's posed. So this is our outline for our strategy. And right about now, you're probably thinking, so what about those hash cans? Before we get back to the hash cans, I want to take this plan out for a spin. Let me make it a little bit bigger there so we can see it. So let's run through these steps on a different problem. This problem says find two positive numbers whose sum is 200 and whose product is maximum. So we just read the problem. Let's make sure we understand it. We've got two positive numbers. The sum is 200, and we're trying to maximize the product. Okay, we do not need to draw a picture in this case, but we should introduce some variables. The reason I don't have to draw a picture is this is not about a geometric shape. It just happens to be about two numbers. So let's name those numbers. Let's call the numbers, something like A and B. So A will be the first number, and B will be the second number. So when you introduce variables, make sure you know what they represent. Since we're not putting these variables on a picture, I wrote a little English description of what each number stands for. Well, now that we have our variables, we can write some equations that relate these variables. The first thing, right in the first sentence, we find out that if you add these two together, their sum is 200. So if I write A plus B, that should equal 200. This equation right here is called a constraint. It's a fact that A plus B equals 200, and it relates our variables. This is not something that we can maximize. The thing that we're going to maximize is their product, and for that I need to introduce a third variable. That'll be the name of our function. So our objective function is going to be P, and that is the product of A and B, so A times B. This is our objective function. That's the thing we're going to try and maximize or optimize. But you'll notice this function has too many variables. We need to have two variables, basically the thing playing the role of y and then the thing playing the role of x. So what we need to do is eliminate one of these variables. And for that, we use our constraint. That is exactly what a constraint's for. So what I'm going to do here is I'm going to eliminate variable b by solving for it in the constraint. So I'll do that down here. A plus b equals 200. That means b equals 200 minus a. So I can replace b with 200 minus a. And now I have a function in one variable. And if I distribute, I just end up with 200a minus a squared. And now we'll do optimization, which basically means we're looking for extreme values. So we need critical points, right? That's what step 5 is asking. We're supposed to find the critical points and the endpoints and test those. So I'm going to take the derivative. P prime is going to be 200 minus 2a. And for critical points, I will set this equal to 0. So 200 minus 2a equals 0. I think you'll agree that means a equals 100. And if a equals 100, that means b must also equal 100, because b is 200 minus a. So the way we maximize the product, if we have the sum of two numbers that's equal to 200, oops, I made a huge error down there. B is 100. Sorry about that. Essentially, both the numbers have to be equal. So the optimum area is a square, is basically what we're showing here. We have the maximum product when we have A equals 100 and B equals 100. 10,000 is the highest product. Let me give you a visual to show you that we have indeed found that maximum. So you can see here I've typed in the function y equals x times 200 minus x. That's the equivalent of p equals a times 200 minus a. And sure enough, here's the top of the mountain. Right? Here's our maximum where x equals 100 and that product is 10,000. So we did locate the maximum value. Now let's get back to our hash can problem. So we've already read the problem, and I want to start writing down some information. The first thing I want to do is I want to draw a picture of one of these right circular cylinders. In other words, a can. So the can has a circular base on top and bottom, and the measurements that are important in a cylinder are the radius and the height, right? So there's my can. The 54 cubic inches, that's the volume of this cylinder. From geometry, we remember that V equals pi r squared h. And if you don't remember, you can look that up on your formula sheet. And so what this is telling us is that our particular volume is 54 equals pi r squared h. Again, this is our fact here. This is our constraint. That's what's going to help us eliminate variables. We still need to talk about what the thing is that we're trying to minimize. And so for that, I go back to the story. And remember, we're trying to save money so we don't get fired. We are trying to minimize production costs by finding the least amount of metal required to make a can. So now we have to use a little bit of problem solving and common sense here to try and figure out what in the heck they're talking about. Here I have a cylinder. How do I figure out how much material it takes to make that can? Well, the deal is this. If you imagine yourself cutting around the top and cutting around the bottom and also cutting down the middle and unrolling this thing, what you end up with is a shape that looks something like this. There's the top. Here's that middle part that we've unrolled, and here's the bottom, right? So this is essentially a circle of radius r and a rectangle. Now the height is still the height, right? If I cut this thing this way and unroll it, it still has the same measurement for the height. But what in the world is this distance right here? Well, for that, we have to think about where that came from. If you rolled it back up, that distance would be the distance around the top or the bottom. And so that's called the circumference, and that distance is 2 pi r. That's supposed to say 2 pi r there, sorry. Okay, so the stuff that we're trying to maximize is the area of these three shapes. We're going to assume that this metal has a constant thickness, so we're not going to worry about the density. We're just going to worry about the area. And if we can minimize the area of these three shapes, then we can minimize the cost. So I'm going to make a new function that's going to be our objective function. I'm going to call it m for metal. And m is going to be the area of the top circle, which is pi r squared, plus the area of the bottom circle, which is also pi r squared. So that's 2 pi r squared. Plus the area of the rectangle, which is just length times width. So that's 2 pi r h. So that's our objective function. Let me write that in here. Which is good to identify, right? But there's a problem. We have too many variables. I can't have r and h in this function, right? This is supposed to be a function with a y, m is our y, and with an x. So I have to eliminate one of these. To do that, if you don't mind, I'm just going to eliminate the h because there's only one occurrence of the h. And I go down to my constraint and I solve for h. So I'm going to divide by pi r squared. And that means h is 54 over pi r squared. And then I'll go ahead and put that over there where the h was, right here. And now my function is m equals, that's supposed to be equals, 2 pi r squared, we did not mess with that, plus 2 pi r times 54 over pi r squared. And with a little bit of simplifying, I end up with 2 pi r squared plus, that's going to be 108 over r. 2 pi r squared plus 108 over r. That's my objective function. That's the thing that we're trying to get to so that we can actually do calculus. I'm just going to highlight it here because what's going to need to happen is I'm going to need to start a new blank slide here where we can finish this thing off. So let me just talk quickly about what we've done and then we'll go and do that. We read the problem. We tried to understand what we were solving. We drew a picture. We labeled the parts of the picture. We introduced variables. The variables helped us write an equation that turned out to be our constraint because there was information given in the story. And the variables also helped us write a objective function, which is the thing we want to minimize. We are trying to minimize the amount of metal. Along the way, we had too many variables, so we used the constraint to eliminate variables. And now we're ready to get some critical points so that we can test those and find out what the optimal situation will be. In this case, the minimum for our metal function. Let me move this function over to a new slide and we'll do that. So once you get your objective function, then we need to find critical points, and we do that by taking some derivatives. I'm actually going to do the first derivative and the second derivative right now at the same time, and we'll use each of those to help us identify and then classify these critical points. So the first derivative is going to be what? 4 pi r minus, because remember 108 over r is like 108 to the r to the negative 1, so that's going to be minus 108 over r squared, because r goes to the negative 2. So that's our first derivative. And then I'm also going to just compute the second derivative here so we can use that to classify once we locate our critical points. So the second derivative is just going to be 4 pi plus, because we bring the negative 2 down, that becomes a plus. That's 216 over r cubed. And before we go any further here, this second derivative in our case, is always going to be positive. So whatever we find is going to be a minimum because it's going to be concave up. The reason I say that is the only place we'll be putting a variable is for r cubed. And the only kind of number we're putting in there is a positive number. So everything's positive. So that's good to note. To note that whatever critical point we find is going to be a minimum. So now let's go find the critical point. To find the critical point, we have to set 4 pi r minus 108 over r squared equal to 0. Technically, we should also check for undefined values, but as you can see here, the only one is going to be r equals 0. And if r equals 0, we don't have a can anyway. So I'm really just looking for the solution to this equation. If I add the 108 r squared to the other side, I can multiply by r squared, and I get 4 pi r cubed equals 108. And that means r cubed is 108 over 4 pi. And frankly, we're talking about the measurements for a can, and I want to send my boss a number that he can understand, he or she can understand. I'm going to assume the cube root of 108 over 4 pi is not acceptable to that person. So I'm going to go ahead and crank that out on my calculator and send them the rounded off value, which should be 2.05 inches. And I think that's going to be close enough to keep my job. 2.05 inches for the radius of the can. Now, I should send the dimensions so that the boss doesn't have to do any math to figure out the height. So remember from the last screen, the height was 54 divided by pi times r squared. And I can plug 2.05 into there, and I can come up with an approximate measurement of the height of the can. And that calculation is approximately 4.09 inches. Okay. So we've read the problem, we've done the math, we've found the minimum values, and more importantly, we've read and answered the question that was posed. The question was, what dimensions are we going to send to our boss? And the dimensions are the radius of 2.05 inches and the height of 4.09 inches. So this is an example of how we use our strategy to solve an optimization problem. These things are not easy. It takes practice reading the problems and turning them into functions so that we can do calculus with them. So be patient with yourself and be patient with me. But there are other videos with other example problems that you can look at, and we'll work our way through this like we do everything else. You know where to find me if you have any questions, and in the meantime, take care.